All right, let's talk about something that trips up so many students, a classic little puzzle in physics, the deal with electric current. We know it has a magnitude, and we know it has a direction, so it really feels like it should be a vector, right? But it's not. So what's going on?
I mean, that's the million-dollar question, isn't it? It's got magnitude, we measure it in amps, it has a clear direction, it flows from a higher potential to a lower one. On the surface, it looks like it's got everything it needs to be a vector, but it's classified as a scalar. In this explainer, we're going to find that missing piece of the puzzle. So where's the catch? Well, it turns out this simple definition of a vector that most of us learn first, magnitude and direction, that's not really the whole story. There's a hidden rule that often gets left out. And this right here, this quote gets to the absolute heart of it. It's not enough for something to just have a size and point somewhere. To be a true vector, it has to follow a very specific set of mathematical rules when you add them together. Okay, so let's lay out the real definition of a vector. It's a three-part test. It needs magnitude, it needs direction, and it must obey the laws of vector addition. Any real vector, whether it's force, velocity, acceleration, you name it, it has to pass all three of these checks. And that third one, that's where electric current fails big time.
So let's put current to the test and see exactly where it falls apart. We've already established it has magnitude and direction. So far, so good. But what happens when two currents meet? Okay, check this out. It's a tale of two additions. On the left, you have two forces. Let's say 3 newtons and 4 newtons, pulling at a 90-degree angle. You can't just add 3 and 4. You have to use the parallelogram law, or Pythagoras in this case, and you get 5 newtons. Now look at the right. You have a 3-amp current and a 4-amp current flowing into a junction. What comes out? Just 7 amps. It's simple addition. The angle of the wires? It makes absolutely no difference at all. And that's the nail in the coffin, right there. Current follows something called Kirchhoff's current law, which is really just a fancy way of saying what goes in must come out. It's simple algebraic addition. It completely ignores the geometric rules that all true vectors have to follow. And that, right there, is the definitive reason it's a scalar. So if current is out, does that mean there's no vector for charge flow? Not at all. We just need to zoom in a little bit and meet the real hero of our story, current density. Current density, which we call J, gives us a much more granular, a much more detailed picture. Instead of telling us the total flow, it describes the concentration of that flow and its precise direction at any single point inside the wire. Think of it as how much current is packed into a tiny little area. This table really breaks it down for us. You see, current, I, is the big picture. It's the total flow crossing an entire surface. But current density, J, is the microscopic view. It's a vector that tells you the intensity and the exact direction of that flow at one specific spot. Sometimes the best way to grasp a physics concept is with a simple, real-world analogy. So let's try one out. Picture a river. If you ask, how much water is flowing past this bridge every second, the answer is a single number, maybe 1,000 gallons per second. That's a scalar. That's your current, I. But if you stick a little probe on the water and ask how fast and in what exact direction is the water moving right here, that answer has a magnitude and a direction. That's your vector, your current density, J. And this isn't just an analogy. It's exactly what happens inside a wire. Imagine the wire gets narrower. The total current, I, has to stay the same, right? Charge can't just disappear. So to get that same amount of charge through a smaller opening, the charges themselves have to speed up. Their drift velocity increases. And if they're moving faster through a smaller area, that means both the current density and the electric field that's pushing them have to get stronger. The underlying vectors are changing, even when the total scalar current is constant. All right, so we have this scalar I and this vector J. How do they actually relate to each other? Well, this is where the math gets really elegant and ties this whole paradox up with a neat little bow. It turns out, to get our scalar current, we actually need 2 vectors to play with. The first is the one we've been talking about, the current density vector, J. The second is something called the area vector, A, which is a vector that represents the surface itself and points straight out, perpendicular to it. And here it is, the magic equation. The total current I is simply the scalar product, you might know it as the dot product, of the current density vector and the area vector. And what do you always get when you take the dot product of 2 vectors? You get a scalar.
The paradox is solved.
So what does that dot product actually do? Well, it's basically asking a question. How much of the flow vector is going straight through this surface? If the charges are flowing at an angle to the surface, the dot product picks out only the component of that flow that's actually piercing the area. That's what contributes to the total current.
And this isn't some obscure idea either. It's fundamental. It's right there in the microscopic version of Ohm's law, which says the current density vector J is directly proportional to the electric field vector E. This just reinforces how deeply connected these vector concepts are at the heart of electricity. Okay, so let's boil this all down. What are the key takeaways? First, current I is a scalar. Why? Because it's a measure of total flow, and crucially, it adds like a simple number, not a vector. Second, the real vector here is current density J, which describes the intense, directed flow at a single point. And finally, the beautiful connection. Our scalar current is born from the dot product of two vectors, current density and area.
And that brings us to one last little puzzle to chew on. After all this, if current I is definitively, absolutely a scalar, then why on earth do we draw it with an arrow in every single circuit diagram we've ever seen? Think about that one. What is that arrow really telling us?